My name is Johnathon Thompson. I'm a student of Dr. Raymond Chow back there, who is still talking to people, and Jay Sharping, who was supposed to come here and give a talk, but he had a family emergency, so he contacted me about a week ago asking me to give a talk in his absence.
In less than a week, you came up with a talk?
Yeah. 2 talks, actually. So 2 talks. They're short. They're 2 short talks. So the first talk I will be giving is a talk about the need to implement quantum corrections in gravity to smooth out the unphysical characteristics of the spacetimes that are present in classical general relativity. The second talk that I will give is just a kind of progress update. There we go. A progress update on some of the experiments that we're doing in our lab. So to begin with, the first talk is, again, related to QED black holes. This is work that I published late last fall in Physical Review D. If you want like a reference to that, I can give that to you or I can send it to you. I am currently writing up an extension of that work, hopefully to be submitted in the next 2 months. So I'll give some brief kind of results of both of those.
So Physical D?
Yes.
Volume?
94. Hold on, let me see.
Page?
It's this here.
Oh.
96.
Physical D 96.
Yep.
No page?
So if you if you just look up, yeah, you should be able to find it. Okay. So specifically what I will show in this talk is that quantum electrodynamics applied to black hole metrics solves the well-posed problem of mass inflation instabilities that occur in the Reisner-Nordström metric. Additionally, I'm going to show that the Cauchy horizon, which is present in the Reisner-Nordström metric, is actually a result of an overextension of the classical results. Additionally, I will show that the naked singularities that are present in Reisner-Nordström are no longer present in the QED picture. We will look at the mass evolution and charge evolution of a black hole. And I will finish up with some discussion of electron. Actually, I may skip that for sake of time. It's a little bit more controversial, so maybe we'll skip that so we can go to dinner. Okay, so as for motivation, again, there are a lot of unphysical characteristics of GR spacetime, such as Cauchy horizons, which lead to mass inflation instabilities. You have singularities that lead to the information paradox, and you have naked singularities that lead to closed time-like curves. So all of these things are not physical. And many people would argue that implementation of quantum mechanics, especially for like singularities, would lead to a removal of the singularity. So the kind of idea that quantum mechanics will smooth out these kind of irregular space-time signatures is compelling. And so what we do in our paper is to look at quantum corrections to the stress energy momentum side of general relativity. Okay? So let's begin. So this is basic derivation. I might go kind of fast through this. You can begin with the Einstein tensor. So this is like how to derive the metric for like a spherically symmetric black hole. Start with the Einstein tensor. This is just the Ricci scalar and tensor. These are just derivatives of the Christoffel symbols, which are also just derivatives of the metric, which you can write like this. So in a spherically symmetric system with no rotation, no time dependence, your metric can look like this. So you just have these functions f of r multiplying and dividing dr and dt. You can write the stress energy momentum tensor in terms of the Lagrangian density like so. So in this way, you can begin with the Lagrangian density that you've specified, and you can work your way to these f of r functions that specify the spacetime. So it might be a little bit confusing. I just wanted to show this to show that you can begin with the Lagrangian density and work out the metric. So the first thing that we can do is we can look at Maxwell. So Maxwell, of course, is just the Lagrangian density is just the minus f invariant, which is, of course, just the contracted version of f mu nu, f mu nu. You plug this in, plug and chug into the Einstein equation, you get f of r that looks like this. Now recall that f of r multiplied and divided dr and dt. So when f of r goes to 0, interesting things happen. So if you solve for the roots of this equation here, which is the Maxwell black hole F of R, you get two horizons, an outer horizon, which is the event horizon of the black hole, and an inner horizon, which is the Cauchy horizon. Now, mathematically speaking, what ends up happening at these two horizons is that space and time switch roles. But like physically what happens if you emit a photon away from the event horizon, it appears infinitely redshifted. If you emit a photon from the inner horizon, it appears infinitely blue shifted. And of course, an infinite blue shift means infinite frequency or infinite energy. And so you can kind of see why this might lead to a mass inflation instability. So it's a lot more complicated than that, but just for like a very simple bird's eye view of like what's going on, that's why the Cauchy horizon is a problem. Okay. So what we're going to show now is that actually the inner horizon is a result of a overextension of classical limit. So in general, you may correct the Lagrangian in...
overextension of the classical limit mean?
I'll show you right now. So the first order correction to the Lagrangian term looks like this. You have this AF squared term. So this is the most generic first order correction you can have. It comes from like the Euler-Heisenberg Lagrangians. It's of course valid for weak fields. If we choose QED, the A will look like this. So Maxwell is valid so long as A times F is much, much less than 1. If it's on the order of 1 or larger, then you have to include higher order corrections. So what we can do is we can calculate the kind of radius at which higher order corrections or quantum corrections become non-negligible. So basically we set AF equal to 1 and solve for R. So this is that R that we get. It's R star. So the next thing that we can do, so now we can plug in the inner horizon radius here. So we do a ratio of R star to R minus. And we choose a charge to mass ratio that's equal to 10 to the minus 18. This is the maximum allowable, it's a reasonable limit, I should say, for the charge to mass ratio of a very massive black hole. This is what is written in this book by Wolf. Now, of course, if we go to small black holes, we can relax this limit a bit. Okay? Now, what this shows is that this ratio, R star to R minus, is really, really large, unless the mass of the black hole is much, much greater than the mass of the universe. So for all realistic black holes that are not that large, yeah?
What happens if you try to drop more charge and once you reach this limit?
This limit here?
Yeah.
You can drop more charge in various ways. Yeah. Mostly it'll repel away. You really have to create the black hole with a charge to mass greater than 1.
Well, presumably you can charge a black hole by dropping protons.
Yeah, but you might get, so it'll depend on how much your charge to mass ratio is initially, but mostly you'll get some repulsion. Okay.
Jonathan, is that Lagrangian, is that just the electromagnetic piece?
This here? Yeah, this is electromagnetism.
That's the contracted Faraday tensor?
Yes, F mu nu, yeah.
Okay, and so there is a space-time piece of Lagrangian that you're not showing. So is that, if I just had one follow-on question, so is that, you say it's a QED correction, is that electromagnetic fluctuations?
Yes.
Because in the normal Reisner-Nordstrom, it's just macroscopic fields, and now you're calling it a QED correction.
It is a first order, like semi-classical correction to the system. It's
still the macroscopic fields?
Yes. Yes.
And all the quantum stuff is in the A?
Yes, exactly. Okay, so the electric field gets altered by QED. It no longer, I can kind of, I don't have it written here, but
I just want to understand what those words.
Yeah. So this is the typical like Maxwell thing, except the electric field is altered a bit because of the QED correction. That's it. So you can actually assume a charge to mass of 1, which is like not so realistic, and you still don't have the R star over R minus is still very, very large unless the mass is much greater than the mass of the universe. Yes?
What's
No, so the only thing that I've shown here...
10 to the 11th times the mass of the universe.
No. So the only thing that I'm showing here is that this, the result of the inner horizon comes from the classical picture of electromagnetism applied to general relativity. What I'm showing is that you can no longer trust the inner horizon because it's well within the horizon at which quantum effects play a role.
Yes.
Okay, that's it. That's all I've shown here.
Oh, okay.
So we have to go to higher order to see if the existence of the Cauchy horizon or the inner horizon is valid. So of course we can do that. We plug in this Lagrangian into the system, and we get an f bar that looks like this. Notice that this scales as a over r to the 6th. Now we want to look at the roots of this equation. However, it is an r to the 6th equation, and sextic equations don't have a analytic solution. So what we do instead is we look at the solution numerically. So here we have the roots of f of r as a log of r plot versus the mass of the black hole. And again, here we show some similar results as before. Turns out that you only have one horizon in the QED picture unless your mass is much larger than the mass of the universe. Okay. In fact, you can estimate, if for large black holes, you can estimate the value of the outer horizon. It looks like this. And notice you just have an extra QED correction term. So it's just a little bit larger than the Maxwell horizon. Okay. So for all realistic black holes, if you model it in QED, there is no Cauchy horizon. So we've avoided mass inflation and stability. Okay. Is that good?
Got a quick question for you. On your previous slide, you had a
This one
statement-
or here?
The one before. You dropped terms implying magnetic monopoles. Why?
Yeah, because they're not real. I mean, yeah. That's primarily why.
Okay.
It doesn't make it any more complicated. You get an extra term here that goes as g squared, which is like f mu nu tilde. You get an extra term here that goes as again an r to the 6th. You just get some correction to this value if you include magnetic monopoles, and you have like a magnetic charge in here. So I've just neglected magnetic charge. So I'm only looking at electrical charge. That's why. Okay. So another thing that we can look at is the evolution of the black hole. The reason why we wanted to look at this is because some people have conjectured that quantum effects might slow down the evolution of a black hole, or at the very end of a black hole's life might leave like a remnant. So we wanted to see what the effect of QED would do to the evolution of the black hole. So this is dmdt and dqdt for the black hole. Notice you have some piece due to Hawking radiation and some piece due to the Schwinger effect. So okay. So you can...
Jonathan, you should tell people in the audience what is the Schwinger?
The Schwinger effect is the effect of having just like a very large electric field such that you get electron-positron pairs out of the vacuum.
Oh, okay. Vacuum breakdown.
Yeah. So you can look at the evolution of QED and Rising-Nordstrom black holes, so I've shown that here. And as one would expect, you get that the QED lifetime is longer than the Rising-Nordstrom lifetime. The lifetime is still very, very large. But it is an indication that QED slows down the evolution of the black hole. In fact, you can show, it's not here, but you can show that the mass evaporation rate per unit time per unit mass goes to 0 as mass goes to 0 for the QED picture. For Schwarzschild, of course, that value blows up as the black hole evaporates.
These are black holes that are evaporating by Hawking radiation, is that right?
Hawking radiation and Schwinger. Schwinger?
Schwinger.
Wouldn't that would imply that the black hole has acquired a charge?
Yes. Uh-huh.
Okay, so the charge sort of stabilizes the black hole.
Yes, that is true. Uh-huh. In a way.
Stops, instead of blowing up like it does in the Hawking picture, it kind of slows down and becomes stable.
Yeah. And
Part of it.
yeah, so I'll mention a little bit about that later. But the interesting thing here, as reported by Hiscock and Weems in their 1990 paper, is that most black holes evolve to extremal the condition at the end of their life. So that's why I started it at an extremal case. Otherwise, the evolution takes a really, really long time. Okay. So one thing that we can do, now we want to look at naked singularities. Again, naked singularities are a problem because they lead to closed time-like curves. And they are admitted if you can somehow collapse a charge to mass ratio of a black hole greater than 1. So here we look at the roots of f of r for a 10 to the 15 Coulomb charge. And we show that there's two horizon, well, one real positive root. We can extend this graph to arbitrary charge to mass ratio. So we can go to 3 times 10 to the 12. And we show that the black hole has one real positive horizon, even for charge to mass greater than 1. So again, this avoids the possibility of having a naked singularity. So no problem with closed time-like curves. Interesting thing from here, though, is that taking charge, you can actually take charge to mass ratio out to infinity, which is the same as setting mass to 0, and you would get a radius still. Now, this is clearly not physical because the fact that you have charge means that you're going to have mass. So there has to be an upper limit. So here I look at what, so very quickly, you can plug in the charge to mass of an electron, and you get that there's a radius of 2 times 10 to the minus 22 meters. However, so just comparing some length scales, the Planck length is 10 to the minus 35 meters. The electron event horizon would be 10 to the minus 22 meters. However, our first order correction is only valid to 10 to the minus 15 meters. So clearly we can't trust this result for the electron anymore. Okay? And I have here the observed electron radius is 10 to the minus 16 meters. So in order to get a value that we can trust for the event horizon of, like, say, an electron, you need a full quantum analysis at these length scales. So I'll skip this slide because it's a little controversial. Now, in order to actually model the system completely, you need to add spin, of course. And the other thing is that in order to make sure that Cauchy horizons and naked singularities are completely absent always in your space-time, you have to look at spin, because spin also causes Cauchy horizons and naked singularities. So this is the work that was done by this group of people here. They looked at BTZ 2 plus 1 dimensional black holes that have some rotation, and they looked at quantum back reaction as their quantum effect. And they were able to show that in this model, it's only a 2 plus 1 dimensional model, but in this model they were able to show that there were no naked singularities, and that the Cauchy horizon did not lead to mass inflation instability. So again, quantum effects are smoothing out the unphysical characteristics of the spacetime. So in conclusion, maybe I'll skip this because for time's sake. But I do want to acknowledge Dr. Munoz from Fresno State. He's the guy that I did most of this work with. I'd like to thank Dr. Chow and Dr. Sharping from UC Merced. They're my thesis advisors for allowing me to spend a little bit of time working on this. I'd like to thank you guys at the Advanced Propulsion Workshop. I have to thank the UC Merced Physics Department travel grant, although they have not actually released the call for grants yet. Because they require this in one of their slides in order to get funding. So I'm pre-thanking them in hope that they will fund the travel. Okay.
Jonathan?
Yep.
Could you go back to your conclusions, because I think that's the part I can understand.
Okay, sure. Yeah. Do you want me to read through them, or?
Well, can you?
Yeah, sure. So basically what ends up happening is mass inflation instability is occurring from the presence of a Cauchy horizon, and classically charged black holes are absent in the QED picture due to the lack of a Cauchy horizon. The inner horizon for the Reisner-Nordström metric, we showed was a overextension of the classical limit. Oh, one thing I should mention here. When we first submitted to Physical Review D, the paper was rejected outright. Like just within like a week, there was a rejection letter, because they said, oh, quantum effects should not have an effect on the spacetime because quantum effects are small. So we had to show them this, that the inner horizon is an overextension of the classical limits. Once we showed them that, then they accepted the paper.
But by overextension of the classical limit, what you mean is that it is that in the range where the quantum effects
Yes,
affected.
yes, exactly. Where quantum effects are non-negligible.
Right.
Right. Mhm. So, but once we showed them that, then they accepted the paper. So, so yeah, it's quantum effects that are avoiding classical instabilities. I didn't show this here, but the extremal black hole for QED has a non-zero temperature. In the Reisner-Nordstrom metric, if you have an extremal black hole, the temperature will be 0.
So you actually answer the rejection, even though the rejection doesn't call for an answer. But
Yep. Oh yeah.
that's interesting.
Yeah. No, I mean that's what you should do, right? So a lot of the people that are going to be on like the PRD referee journals, stuff like that, they look at something like this where you've removed something due to quantum mechanics that everyone knows is there, and they're going to say, oh, this is clearly wrong because quantum effects are small. So you have to like show them. So what we did was we actually wrote up another 2 pages to the paper where we addressed all of the referees' complaints. And then we resubmitted and we sent a letter to the editor saying like, hey, look, we addressed these issues, and then it was accepted. Yeah?
One would have expected there to be medium-sized black holes created at the Big Bang that are just now getting around to decaying and producing explosions with lots of charged particles that should be visible. Do you have any explanation of why we don't see anything like that?
Like an explosion of.
Well, you know, the last phases of the decay, they become super hot and begin emitting all kinds of heavy charged particles.
But that's not necessarily the case. So what we showed here is that the end life of the evolution slows down. The MDT per unit mass goes to 0 as mass goes to 0.
Does that mean they don't evaporate or something?
They do evaporate. They do go to 0. There is still like an evaporation, but they don't.
They don't burn out, they fade away.
They fade away. Yeah, there isn't this.
They don't emit very massive particles while they're decaying. So what is coming up? Just electrons and positrons and photons?
Mainly, if all you have is mass, it's just like photons. Yeah. But then, I mean, so the actual calculation of the temperature involves like all massless particles.
I think that's an important point. Maybe you should write a separate paper pointing that out.
I am, yep. That's. So there's a couple of things that I'm going to write up in the next paper. One is this. So the things that I wrote in the first paper were these top 4 things. I guess through these top 5. These 2 things here I did not put in there because I wanted it to get published. And having too many things in the paper that calls like a red flag, and it's really impossible. So one step at a time, I guess. So my next step, is to look at this and to talk about the electron. Yeah.
Let me just see if I'm understanding this. By associating charge with mass, and then there's of course, the Hawking instability, but then there's also the Schwinger instability. It sounds as if the Schwinger instability is the thing that really drives this stabilization of smaller black holes.
I don't know. Maybe that might be true.
Okay.
Can we go to the next one?
Okay. Yeah, I have one more talk. Okay. Oh, well yeah, this is how you know I'm primarily a theorist. I can't even work a PowerPoint. So if there's no other questions on the black hole stuff, I'll move on to the experimental slides. So for the experimental slides, this is most of the work that is being done by this large group. We primarily work with SRF cavities. There's superconducting radio frequency cavities. And we're looking at ways to do optomechanics in these types of cavities. So at a very high level, what we're trying to do is dynamical Casimir and dynamical Casimir-like effects. So if you can imagine, you have 2 boundary conditions for the electromagnetic waves, and you oscillate one of these boundary conditions rapidly enough, you're changing the if you oscillate the boundary condition fast enough, you'll create real photons out of virtual photons. And so that's the dynamical Casimir effect. So kind of like what we were maybe trying to do in our lab is the following here. We insert an 11 gigahertz signal into this pump cavity. It has high Q and high coupling to this membrane, so the membrane moves. This membrane motion, if it's fast enough and above threshold, will create photons in this cavity here. And if you can take some of those photons out, these are dynamical Casimir effect photons, you take them out, you can do some interesting things with them.
What's the membrane? Can you explain more about the membrane?
Yeah, so I will in a couple of slides. I actually have like a picture of the membrane, but it's silicon nitride membrane. It's about 500 nanometers thick with a niobium coating of 300 nanometers.
How thick is it?
500 nanometers of silicon nitride and then 300 of niobium.
And have you actually observed the motion?
Yes, for small frequency, not at 11 gigahertz or 22 gigahertz frequency, no. But yeah, so we'll. Actually, I don't have slides on that, so I will describe it. I'm not on this paper, but Luis Martinez is like the author of that paper. He looked at driving a membrane like this into motion at its fundamental resonance of 6 kilohertz. And so he was able to show like a nanometer of displacement by inserting 11 gigahertz signal and two signals that are split by like a 6 kilohertz. And yeah, so you can get some like motion here. So he did show that, but nothing at 11 or 22 gigahertz. Okay, so the main goal is to create a cavity with a high enough quality factor so that we can build up enough energy into the cavity so that our coupling rate to the membrane is large enough that we can do interesting optomechanical experiments. So we're not the first people to look towards cavities to do experiments, of course. The first people to use these types of SRF cavities were in the accelerator field. The Walther group did some really good atom cavity experiments. So a picture here. The Hirosh group did some really spectacular cavity building here. So what they have here, this is the bottom half of a cavity. It's a Fabry-Perot cavity, so it's an open cavity, and you can send atoms through the cavity. The most impressive thing about this Hirosh cavity is that the Q was 10 to the 11. So this is an open cavity with a Q of 10 to the 11. So very, very impressive. So the fact that the membrane motion has, or I guess the resonance of the cavity is very sensitive to the membrane motion, gives you like obvious applications to metrology. So Charles Rees did some experiment here where he had a vibrating end wall and 2 coupled cavities. So in a coupled cavity system, you get a spectral doublet. And because you have a spectral doublet, you can enhance mechanical effects from the membrane. So what he was able to do is parametric frequency down conversion. So you send a signal in here at the upper resonance, and you vibrate the end wall at the splitting frequency, and you can get down conversion into the other frequency. More recently, work has been done in quantum information by the Sholkoff group and Still group. And basically what they do is they look at qubits. They put qubits into the cavity, and they look at the interaction between the cavity and the qubit. Okay, so these are the types of cavities that we're looking at. So here's a cylindrical cavity with radius r and length L. The cylindrical cavity has a bunch of different modes, but we primarily work with the TE011 mode that's mocked up here. This is the electric field of the TE011 mode. Notice it's, huh?
Why are you working with TE0?
Oh, yes, because it has been shown to have the highest quality factor in these types of cavities. So we have a donut shape, and then this is the corresponding magnetic field. Notice here that it's the magnetic field that's going to apply pressure or coupling to a membrane. So we're typically, we're going to add a membrane to one of these end walls. So it's the magnetic pressure that gives us membrane motion. We've also been working with quarter wave stub cavities because they actually give a higher quality factor even than the cylindrical cavities. So here's a stub cavity. So you have a conducting bottom plate with a stub here, conducting stub. And the resonant frequency of these cavities, or the wavelength, is equal to 4 times the length of the stub. The electric field is centered around the tip of the stub, and the magnetic field is centered around the bottom of the stub here. So each of these types of cavities have their advantages and disadvantages. So the cylindrical cavity has the advantage of being conceptually simple. All of the calculations we do, whether it be G naught or frequency, we can calculate analytically. And it's simple to machine. And you can integrate a membrane very easily by just putting a membrane at one of these end walls. So you can get some coupling rate, some frequency pull parameter. So I mentioned this frequency pull parameter. I'll mention it again later, but just very quickly, the frequency pull parameter is the amount by which you can shift the resonance due to membrane motion, or the motion of an end wall. The drawbacks are that it's low Q.
How low?
10 to the 8.
Ooh, that's terrible.
It's better than 10 to the 11th.
It's worse than 10 to the 11. So the coaxial stub has the advantage of being higher Q, and it can be built out of one piece, so you don't get any seams. So you can just come in with an end mill and drill out this, and you just have one cavity. You can actually, so I'll show in a couple of slides, you can actually, out of one piece of material, make several stub cavities.
So it is 10
pretty
to
small.
the 11, the Q?
No, this one's not. So I'll show the results in a couple slides, but we were able to achieve 10 to the 9 in one of these cavities, and 10 to the 8 in one of these. So the drawbacks of the...
The SRF community has demonstrated 10 to the 11 for the cylindrical cavity. Okay? So it's well-established technology to produce cubes of 10 million.
Okay, so the drawback of the stub cavity is that it's kind of hard to integrate a membrane or a mechanical element into the cavity. So it's hard to figure out what a frequency pull parameter might be, because the maximum electric field is here and the maximum magnetic field is here. So where do you put the membrane, or where do you put some mechanical element? It's kind of hard. And plus these things are pretty small, these ones. Okay, so quality factor and frequency pull parameter. I just wanted to highlight why these are important figures of merit. So to do any type of good optomechanical experiment, you have to have a large scattering rate. So the scattering rate looks like this. It's 4 G naught squared N cavity over kappa, where G naught squared is the so-called zero photon coupling rate. So you can imagine it as you have just vacuum fluctuations in the cavity, and how much is that going to change the resonance, which is vacuum fluctuations. So of course, if you include extra energy into the cavity, then you increase the amount by which you can shift the frequency. So the idea here is to do any good optomechanical experiments, you want to be beyond the line width of the initial resonance. So it's known as the resolved sideband regime. And you can kind of see why. You're moving the resonance far enough away from the initial resonance that you're beyond the sideband of it. So that's why those figures of merit are important. You can rewrite this scattering rate in terms of G naught and Q squared, as a proportional. So the higher our G naught and the higher our Q, the better our optomechanical experiments will be. Okay. So that's what we're trying to do. So here is a kind of mock-up of what we do in our lab. So this is a model of our dilution refrigerator. So we have our cylindrical cavity down here at the 30 millikelvin plate. We have some attenuators to isolate the thermal noise. So then we also have low noise amplifiers here. So this is the silicon nitride membrane here, shown here. We have these capacitive electrodes here. So this is the actual ones that we can use to drive the membrane motion and sense the membrane motion. So that's kind of the mock-up of what we do. So our best cylindrical cavity results are here. So again, we have the cavity that's 1.5 inches in diameter. And so the membrane that we have on here is coated, it's 500 nanometers of silicon nitride. The resonant frequency of this cavity is about 10 to the 5 gigahertz. The fundamental frequency of the membrane, the first order oscillation of the membrane, is 6 kilohertz. So without the membrane, our best cavity Q was 3 times 10 to the 8. Once we put a membrane here, the Q dropped to 5 times 10 to the 7. And our coupling rate, we calculated to be 10 to the minus 6 hertz. So our Q is still pretty good, but our coupling rate's a little small. Okay. So we've actually been improving Q over the past year. So from what we understand, the best way to improve Q is to pick the best materials. So we pick triple R and niobium, and you have to do some material treatments. So we do a BCP etch and then a bake, and that gets rid of the most of the impurities.
John?
Yep.
Can you verify which mode you're running at? Can you measure the electric field? Is that you can?
So the modes are so far separated that's not an issue. But yeah, you can.
And the Q being so high, it's so narrow the bandwidth that allows you then to have a lot of effective separation. High Q, low.
This reminds me of the Axion dark matter experiment. They use TE01 as well, except it's much larger. They use a low frequency. The cavity looks similar. They've got
I
bottom.
think, didn't someone from the dark matter Axion group come to our lab at some point? You're talking about the ones, the work out of South Korea, or?
They're at the University of Washington, and they do have a similar mechanism.
Oh, okay,
Except
okay.
it's much bigger.
It's bigger, and it has to be in a magnetic field. That's the main problem.
Oh.
There has to be a magnetic field that converts axions into microwaves, and then a cavity that detects the microwaves.
I see.
So that makes the light bulb. Having to have a magnetic field makes light bulb complicated.
Yeah.
John, who's the guy at Seattle?
Leslie Rosenberg.
Leslie Rosenberg.
Yeah.
But these are theoretical actions.
No, it's a big project. They've been running for.
Did they find anything?
Huh?
Did they find anything?
They have to sweep and look and sweep and look and sweep and look, and
No, they have not found.
and they have not found any results at
They have not
all.
found it. They have not found it.
No, and they probably never will, but. But I think it's a noble effort, and it would be wonderful if they did. And they, in terms of what the limits of their sensitivity versus what the theoretical predictions are, they're really right at the right point to be able to see something. So if they're there, they should see them.
Okay, so the thing that really limited our Q, so we were expecting Qs that were a little bit higher. I mean, they were high, but we were expecting Qs that were higher, were the seams in the cavity. We had to build it out of 3 pieces, and especially with the membrane integration, it becomes really hard to keep I mean, the seams themselves lead to loss, but even more importantly is you have to get it all lined up correctly, and it's kind of impossible to get them lined up perfectly, especially when you're dealing with Qs of 10 to the 9 and stuff like that. You have to have it perfect in order to maintain those. We've also been looking at improving G0. Over the past 6 months, we were actually with some novel cavity membrane designs. That's one of the ones that Dr. Chow showed with the pointed stub. We were able to achieve 3 orders of magnitude improvement in our G0 over the past 6 months. So we're about in the range where we can start doing some interesting optomechanical experiments. It's just, once you get something working, getting it working again is kind of hard. But so here is our best results for a stub cavity. Here's like a typical measurement to figure out what the Q is. So you send a power pulse into the cavity, and you look at the ring up and ring down of the energy in the cavity. And so you can see here that that your tau, or your ring down time, is about 10 milliseconds for a cavity like this. So it corresponds to a Q of about 10 to the 9. It's actually 2 times 10 to the 9, but so this is our kind of best results. Again, we just need to figure out a way to implement some mechanical element in here. We also look at coupled cavity systems. We do this because once you couple a cavity together and then you put a membrane in here, the coupled cavity system can enhance the mechanical vibrations, or the mechanical effect. So in this system, you can couple the cavity together by just using like a wave. And so in order to see that the cavity is coupled together properly, you do a avoided crossing measurement. So basically what you do is you take a dielectric And so what we did is we inserted a dielectric into this cavity to tune the resonance of this cavity. And so what ends up happening is if you don't have any coupling, you're tuning the cavity so your resonance, moves up like this straight. And the other cavity just stays flat because it's not being changed. But if they're coupled together, you get some avoided crossing when their resonances are very close to each other. And that's due to, the avoided crossing. So we were able to achieve that too in these types of cavities. So in summary, this is just a kind of progress report for the experiments that we're doing in our lab. We are near unity in the scattering efficiency now. We were able to produce high Q cavities. Our next steps are, of course, to get good enough values so that we can do some electromechanics in the cavity. So what we want to look at is sideband cooling of the membrane. So sideband cooling, of course, is you have a membrane with some resonance. You can insert a pump signal into the cavity that's detuned from the resonance of the cavity by the membrane frequency. And because of that, your initial photon that you insert has to borrow a phonon from the membrane to become a photon of the frequency of the cavity. And so you get a lower phonon occupation state in the membrane. So that's what one of the next experiments we're going to try and do. And then also mechanical coupling in the stub cavities. So one of the most interesting things that we kind of thought of was putting a levitated magnet on the tip of the stub. So if you look here, take a magnet and put it on here, like a little tiny magnet, and then you take it through the transition temperature, and because of the Meissner effect, it should float. So you should have a floating magnet in here. And of course, the floating magnet will have some intrinsic oscillation. And because of it might rotate, so then the rotation will have some oscillation. So you might be able to do some cool electromechanical experiments like that. Here we show it looks like it, yeah. It's actually 6 stub cavities machined onto one piece of metal. It does look like a gun. I think the name that someone gave it was like a
revolver.
Yeah.
Well, the original magnetrons developed during World War II were 6-sided, and they used the drum from a revolver.
Oh, okay. That's interesting. Yeah, but so we do this so that we can get a very replicable way of figuring out what types of things change the Q factors of these cavities. So each of these cavities is a little bit different. These two are coupled together. Some of these have stubs that are pointed. Some of them have stubs that have holes in them and other things. So this is kind of it's nice because these things are small and you can machine them out of one piece of aluminum, and it's really cheap. So I guess that's it for the experimental update. You guys have any questions?